Well, good afternoon. I want to welcome everyone to our solar webinar today. This is for those of you that are new to the program. I'll just mention now that this is part of an ongoing webinar series. We've touched on several topics to date. It's a weekly program running on Wednesdays at 1 o'clock. I'll mention some of the programs we've touched on in previous weeks. Going back the last 2 weeks, we've talked about the solar market in the state of Maryland, and we've talked about the basics of solar PV technology, looked at some of the components last week. If you missed some of those earlier sessions, you're welcome to go back and review the material and the recordings from those sessions. They're on our website. It's at extension.umd.edu/energy. But I'll just provide a little bit of introduction while we await some additional individuals to join the program today. So as I mentioned, this is the third session in the series. Today we'll be talking about solar planning and design. And I'll take this moment to kind of give an introduction to those of you who have not met me before. My name is Drew Chavone. I'm an energy specialist with the University of Maryland Extension. My background is in agricultural engineering, working in a variety of energy conservation and technologies. So I'm particularly interested in today's session and approaching that. From time to time, we'll address things and have additional speakers come online for our weekly series. Next week, for instance, we'll be talking about regulations, permitting, and zoning issues from a small scale and up into a little bit of information on utility scale, larger solar systems that you may or may not be interested in, but there'll be a variety of topics and hearing from additional speakers as well. But with that said, today's topic dealing with solar planning and design, we'll touch on some of the design considerations that you'll take into account in installing a solar PV system. And so I think we're still having people join, but we'll try to stay on schedule today and make sure that we have time for questions towards the end of our hour together. So again, my name's provided here on the presentation if you have the screen in front of you. The website again is extension.umd.edu/energy. If you'd like to find out about more of these sessions, register for sessions next week and the coming weeks. If you haven't already, you can go to the website and register there. There's a number of other resources on the website as well. Topics ranging from saving energy in your home to other commercial and other things, biomass and other technologies as well. But we'll get started on our program today. Quick note just on the logistics here. I noticed that I missed some questions last time that were in an area I wasn't looking. So try to get your questions in the Q&A box. And like I said, I'll try to address some of the questions you may have towards the end of our session today. I think the chat function should be disabled just so there's not confusion. So if you click on that and you're wondering why it's not working, it's perhaps because I've closed that down. So try to get in this question Q&A area, and I'll touch on those as we move forward. But just at any point, put those in there. I'll mention now as well that session is being recorded as each week is, and so if you missed part of it, you can go back and review that as well. Now, as I do every week, I'm going to launch a survey, 2 questions on there just so we have a better idea. This is anonymous, but we'd just like to know who's joining our program today. So if you have your computer, you can go through and look at these 2 questions. Tell us, and you can pick multiple options, but just take a minute or 2, tell us kind of what your interest and background is. If you're coming from a farming background or from the solar industry or academics. And then question 2 is any specific applications you're interested in. Are you interested in any certain technology? And that'll help guide future programming that we do. So when you're done with that, please make sure you click the submit button, and then we'll jump into the content for today. Okay, I'll give you about 10 more seconds or so to get your responses in. Appreciate everyone's input. Okay, Well, with that said, let's look at what we're going to touch on today. Touch on various topics. A bit of where we'll start today is a recap of last week and talking about power and energy. And why we're kind of revisiting this topic is because when we go to design and size up the solar PV system that we're going to build, and let me just back up for a minute and reiterate that as an employee, an extension educator with the University of Maryland, I'm not a salesman in any capacity. And it's not my intent to sell you a solar system and have you install it as if it's a silver bullet technology. So I just want to emphasize that and be upfront with that. What I'm here to do through this webinar series is to share some unbiased research-based information that helps you make an informed decision. So, you know, I just want you to have that in mind, that I'm not going to say, and you'll hear me reiterate over and over again through this webinar today and through the rest of the series is, you know, I don't intend for every one of you to install a solar PV system. I don't think it'll work 100% of the time in every application, but we'll kind of start to wade through some of these options. So I'm just going to put that out there now so I don't forget. But as we get started, we're going to talk about power and energy. And it's important for us to know how much energy that we're using on site, whether it's on the farm or in a house. How much energy are you actually using is going to dictate how big of a system you need to design. And sometimes we'll be able to weigh, well, we can cover 100% of our energy or maybe 50%, and we'll start to weigh some of those options. So that's where we're going to kind of start. There'll be a little bit of recap from last week, but some new information as well. I have included a little bit of math here, so don't get scared away just yet. It's not as complicated as it might seem at first. But we discussed the definition of power and energy last week, and really what I want to draw your attention to this week and through the session today is the importance of understanding how much energy you use. Again, how much energy is being used on the farm or home, that's going to dictate how big the system needs to be to supply that energy. You'll see energy is quantified in the units of watt hours or kilowatt hours. Many of you will be familiar from seeing that on your utility bill. Kilowatt hours is the energy, you know, what you're getting charged for and what you pay for. And so your utility provider will charge you depending on who you're with. You know, in my area, it's, you know, about 0.07 cents a kilowatt hour. So we'll kind of touch on some of the economics today, but especially moving forward into subsequent webinars, we'll talk more about the economics. But just so we understand difference between power and energy, I've included a couple examples similar to what we looked at last week. I won't highlight all of them, but what I do want to point out, and I'll see if I can kind of highlight, you know, let's look at the example in the middle is for a light bulb. And so if you look at the light bulb, it's usually stamped right on the bulb itself is that power rating. So in this case, it's, my highlighter is not going to work, is it? Let me try now. About 60 watts, that worked better. So for this case, the power of the light bulb is 60 watts. But what you're getting charged for is the actual energy that's using. And the energy that light bulb uses is based on how long it's turned on. And so for this example, all I've done is done a simple situation where I run the light bulb for 4 hours every day and 365 days a year. Okay, so conservative estimate, but if you crunch the numbers on that, in this light bulb example, it's 87.6 kilowatt hours of energy each year. Okay, so if you use the light bulb that amount of time, that's how much energy you supply. And so what you'll see is they're kind of starting from a basic level of device by device. And in some sense, you could perform an energy audit and determine for each device within your site that you're going to analyze the energy use for. So we're just going to start at this basic level, then we'll scale up and see for a whole, you know, one single site. And if you're looking at your barn and your whole farm operation, how much energy is that whole system using? But we'll look at a small scale first. Just to compare and to reiterate the difference between power and energy, I've included this television It's an LED TV. It's got the same power rating as the light bulb. You see 60 watts as well. What's going to make a difference, though, is how often you use these two systems. So in this example, I've said we'll watch a movie for 2 hours. And if we do that every week, run the numbers on that, and you get 6.25 kilowatt hours from through the course of the year. So you see two systems, the light bulb and the TV, they both have the same power rating, but depending on how often you use them, gives you a different energy consumption at the end of the year. Okay, so I just want to point out that hopefully that kind of makes sense, especially if you were able to join our session last week. We spent a little more time on that. Provide a couple more examples before we get into the actual design of a PV system to meet some of these demands. Picture here is just measuring the voltage and current for a light bulb. And you could use a multimeter for this if you don't have the power rating for a device in front of you. I have a motor in my workshop, and the actual power, the label that's attached to the motor has been lost. So there are ways, of course, that you can look that up if you have the owner's manual, or you could use a multimeter and you can determine what the power and then subsequently what the energy is. There's ways to do that, and this is hooking up a little watt meter to a light bulb, again, to find out how much power it uses. So in the case on the left, it's turned off, there's no current flow, and if you multiply voltage times current, that gives you the power. And so in the case on the left, the light bulb's turned off, there's no power because there's no current. But once that current is activated, your power goes up, and in this case, it's a 60 watt light bulb. At least on the shelf, that's what it says, but with an actual measurement, it's close to that, but about 67, 68 watts in this case. One additional example I wanted to share of lighting demand and kind of a precursor into what we'll talk about with energy conservation and efficiency. If you look at these three different types of light bulbs, and I'm sure many of you are familiar with the idea that LED light bulbs, and the price of those have come down significantly, but LED light bulbs are much more efficient than your old-fashioned incandescent bulbs, as well as compact fluorescent. So there's some benefit there to having energy efficiency, and I'll kind of continue to cycle back to that idea of energy efficiency, because the more efficient equipment you have, in the case of this LED, if you have all LEDs, you're saving on energy. Not only are you saving on the cost of that energy, but now if you're designing a solar PV system, you can scale that system down a little bit. You don't have to invest quite as heavily in the solar technology if you're using less energy. So there's some importance there. So I've put a table there. You should be able to see that the power rating for the bulbs decreases as you start to look at the LEDs. It's a lower power, and as a result, if you're running all three of these light bulbs for the same amount of time, the LED is obviously going to use less energy in the end because the power is lower. And there's some cost impact as well. As I mentioned, my rate is about 0.07 cents or 0.07 cents, 7 cents a kilowatt hour. So quite a bit of savings there if you talk about the LED over the course of a year. This is what's shown. So where a incandescent bulb would have cost you, $7.50, we're now under $1 total for that LED bulb for the course of the year. So again, that's the importance of saving on energy first before you invest in an expensive technology like solar photovoltaics. I do want to point out kind of some of the variability in some energy loads that we have, and I've included some household examples here. On the right is refrigerator, and I won't spend too much time talking about these examples other than the fact that, as I said, these systems have variable power use, and so all of them have some background level of power, whether it's to run an LED light for the clock on it or something like that, or a light bulb inside of it. When you think about the refrigerator in particular, you have the compressor kick on at certain times of the day for that chilling to actually happen. And so you don't have the same power throughout the course of a day or throughout the course of a season. You're going to be running the equipment at variable loads. And so what I've just tried to indicate is the difference between, if you look at the far right with the refrigerator, you're getting a reading of a 7.9 just with background power. If it's just sitting idle. But when the compressor for that refrigerator kicks on, you jump up to about 1400 watts. And so you'll see that it's kind of important that we're not just looking at instantaneous energy use or power. When we look at energy, it's over a certain time. And when we actually start to talk about how we design the PV system around that, we typically look over an annual period and we capture some of the seasonal variation as well, more so than just a local demand, because we might miss some of the features that we see with different equipment. So, you know, that's kind of a small scale how you can look at individual devices. You could have a formal energy audit performed on your farm. If you do so, I'd recommend getting someone that has experience in the farm industry, and I could make recommendations on that. If you're interested, just reach out to me. There are other ways to get energy use. You could do your own audit and kind of go around and quantify the lighting, chilling and refrigeration and other aspects of ventilation. There's some other resources I just want to point you to if you don't have the ability to measure that power in any system. You can look it up online in the owner's manual. You can go to their website. I've included some information here from the Energy Star website. If you have any equipment, just as an example, that has an Energy Star efficiency label on there. I pulled up an example of a refrigerator on there. I just picked a random one, General Electric refrigerator. And what you'll see is it has an energy use, an annual energy use of 442 kilowatt hours. Okay, and so that's just another way to go about quantifying the energy use of any piece of equipment that you have. You can get that in various ways. One additional way is just go right to your bill, your monthly bill that you get, and you know, depending on who your utility provider is, it'll look a little different than this. Whether you're on BG&E or Potomac Edison, it always looks a little bit different. But I've highlighted an example here, and the important part I've tried to highlight is the monthly energy use. And so this is kind of an easier way than going around and doing a full energy audit on your property. You don't get necessarily an idea of each device, but you get the overall energy use. And so, you know, if you look at this chart, you'll see it starts with June and it gives you the output or the energy that you used in the month of June, 548 in this case, if you can see those numbers. And so month by month, it gives you some energy use. What you'll see in the fall months where we are now, in that middle region, energy use is a little bit lower. From this example, it kind of looks like in the winter time, they might have electric heating or something like that. And so you get a little bit of bump up in the winter. And so, as I mentioned, you'll see some seasonal variation in your energy use. But as we start to design the PV system, we're going to take all this information together. And so in this case, they do not provide a annual energy use. It's just month by month. Yours might have that, but this one did not. In this case, I just copied those data points over into an Excel spreadsheet. Okay, and I just added these up together. Once I added all these together, I got the total annual energy use as 5,592 kilowatt hours. So that's a pretty easy way just to go and evaluate how much energy you use over the entire year. And I'll mention with this particular example, they provide 13 months of data. Just make sure you're only looking at 12 of those. And that's what I've done here in the example. But that, again, is just an easy way to know what your energy use is. And that's the first step to understanding what kind of a system you're going to design. Now, to go back to the topic that I've brought up about energy conservation and energy savings, it's very important. What I often kind of go back to is prioritizing that low-hanging fruit. And what I mean by that is looking at this pyramid triangle. focus on the bottom levels first, because those bottom levels are going to have your best return on the investment. You know, so at the bottom is just kind of an analysis, and that's kind of just thinking through the process. It might include a formal energy audit, understanding how much energy you're using, but really the first step that I want to point out is having to do with energy conservation. And energy conservation simply means you're not using the energy. So an example would be turning the lights off when you're not using them. Okay, it costs you nothing to do that. It's more of a behavioral change. But if you save on energy up front like that, then again, you're saving on your kilowatt hour charges, and you're also having to design a smaller PV system if you end up doing so. Okay, and so that'll save you a lot of money up front. If you continue looking from the bottom upward through that diagram, you'll see efficiency is important as well. Again, the light bulb example of an LED is more efficient. It uses less energy. It's also a very affordable option to implement. Time of use management, we'll touch on it from time to time in today's webinar and subsequent webinars, but more so if you have different pricing structures in your region or from your utility provider. If you have a time of day like in the afternoon when you're charged billed a higher rate, you might want to offset and compensate some there. But lastly, at the top is what we want to focus on with renewable energies, not as a, I don't want to say as a last resort, but in some ways there's some truth to that, is try to focus on these easier, better return on your investment technologies, conservation, efficiency, management, before you look at a renewable like solar photovoltaics. And so I just want to say that before we dive too deep into the design work here. And I've just shared a few typical results, which you know your farm might look a little bit different, and from region to region within the state and throughout the greater region that we're in here. But just for a typical case, what you'll see is for a lot of applications, your heating and cooling and ventilation, all your HVAC equipment typically uses the most energy. So if you're going to start conserving and saving on those, you probably want to focus on HVAC, any of those systems. The same applies to, you know, a home or an apartment. You typically want to focus on those. Lighting is a smaller piece of the puzzle. Of course, LED lighting is helpful, but you typically want to focus on heating and cooling systems and that kind of thing. And so I'll briefly share some tools and resources that'll help you get started on that and saving energy and understanding the energy use. Again, if you go to our Maryland Energy Extension website, you'll find some resources on there, including an energy log, and that'll help you to record how much energy you use. The spreadsheet, you can download that if you enjoy working with spreadsheets. And you can put your information in there, not only for electricity, but if you use natural gas and other fuels, and it'll give you a nice kind of picture of what your energy use looks like over the year, and you'll be able to kind of target specific areas. You know, for instance, if some of your motors and other things are not working at 100% efficiency, well, they'll never work at 100, but if they're not working as well as you think they should, you can target some of those areas and try to cut down on your energy use. I'll share another resource as well. This system, this is from Wyoming Extension. It's a little bit neater and cleaner looking than what we have on our website, but you can print this form out. You do have to do the math by hand, but it might be a little easier to follow if you're not too keen on the Excel spreadsheet. But just another way to quantify how much energy you are in fact using on your site. And so you can look at different pieces of equipment and run the numbers on that. But there's more information. There's a link there to their website, and if you miss it now, this information will go on the recording, and you can check that later. So that's kind of the importance and why I want to emphasize the importance of energy savings up front. And now we'll kind of jump into some of the considerations once you kind of have an idea of that on how you assess your site and some of the considerations that'll come into play there, from orientation to tilt and other things like that. First thing I'll point out is just making sure you have enough solar resource. You have to have enough sunlight, and really for most of the country, that's true. There's some variation, and I've included a graph here, or a map from the National Renewable Energy Lab, NREL. You'll see, of course, there's more solar irradiance down in the Southwest from through the seasons, but what I just want to indicate is that we do have significant resource here in Maryland and in the region, enough to make this a very viable technology. I have highlighted specific examples just from cities around, just to get an idea. We're kind of talking about a very small range, 3.5 up to, you'll see 6.5 kilowatt hours per meter squared. So it's kind of a small range, but there is some difference in different geographies we'll talk about. You'll see I've highlighted in the table what's typical for Annapolis, Maryland, and a little bit lower down, you'll see Frostburg, where we're farther west in the state, is a little lower. The one thing I will point out is you know, a common example that's brought up is what's happened in Germany. Germany, if you look at the bottom of the chart, Germany, and it's not shown on the map, of course, but Germany has a much lower solar resource than even Frostburg, Maryland has on average. But yet they have, you know, in recent years, not so much anymore because they're kind of at their capacity, but they've led the way in solar implementation and really installing quite a bit of solar throughout their country. And even though they don't have as much resources as us. So with that said, I just want to show we do have a competitive resource available to us to make this a viable technology. So we're not going to talk too much about that. I'll highlight some of the importance as we start designing a system. But if you want some more specific information, I've included a link here to the NREL website, nrel.gov, and you can look at their handbook data manual here. I've pulled up what Baltimore looks like, and what you'll see in the middle here, the middle graph, what you'll see is that solar radiation does change through the seasons. I've said that from time to time, but you'll notice that, you know, in the winter months in January, you have a lower solar radiation level. But if you're looking in June and July in the summer, you're going to have a higher level. That's, again, some of the importance of looking over the entire annual time frame to get an idea of some of that variation and incorporate that. If you look at the data tables in this data manual, what you'll see is a number of values given for solar radiation. You also see them given as a function of the tilt angle, and we'll talk about that. If you lay your panel flat down, you know, flat on the ground, you know, have it pointed up, of course, but if you have it laying flat, it's not going to be as efficient, and you'll see that reflected in the values in this table. And so we'll talk about the tilt, but if you want specific information, you can use resources like I've shared here to get more of a local level of the solar levels. So the importance of orientation, and I'll just kind of mention the sun obviously does change, obviously from daytime to nighttime. The sun rises in the east and it goes down in the west, but it also changes seasonally. And so you'll notice that the sun is lower in the winter time, follows a lower course. Going into the winter months now, you'll see it start to set and stay pretty low in the sky. So there's some seasonal variation, and which way we point the solar panels is going to dictate how much energy we get out of the system. You really never want to face it north. I'm assuming most of us on the program today are in the northern hemisphere, and of course in the United States we're going to be seeing the sun to our south. So for most applications, you want to point your solar PV system to the south, and you're going to collect the most radiation that way. And that's regardless of winter and summer changes, because it's always south of us. You'll see in the pie charts on the left, you know, if it is pointed north, you're really not taking advantage of, you're not really taking advantage of that southward sun. And so you're not going to get the efficiency levels that you would with a south example. So in the south example, if you have your panels pointed southward, you'll get the highest efficiency. You're going to maximize that solar radiation that's coming into the panel. There are some cases where maybe if you're doing a rooftop system, for instance, if your house is not aligned properly, some people will opt for a ground mounted system where they have more flexibility, or they may even try to change the angle to be oriented more south. I'll say there's some caution to practice there. If you're trying to orient south and your roof's not really in the right direction, it will cost a bit to invest in more racking and rails and everything to kind of get that orientation fixed. Even when we talk about tilt, there's some added cost to that as well. So I don't necessarily recommend doing that. Of course, if it's north, you're not going to have that great of a system, and you might want to look for some other options. But if you're a little off to the east or west, it's not too big of a deal. But we'll look at some more examples as we go forward. But again, I would say your safest bet is having your panels face directly south, and you're going to get the best efficiency from that. So just another way of looking at this diagram, I've highlighted that south direction there in the figure. You can see that red line pointed in the south direction. Again, like I said, you could tilt it a little bit if you need to the east or west. I've heard of some cases where you might go a little bit west in order to capture that afternoon sunlight. Remember, the sun sets in the west, and so if it's a little bit oriented to the west, you'll get a little bit more sunlight in the afternoon hours, and that could help if you're being billed a higher rate during that time or using more energy during that time. I'm not going to say you should always do that, but there are some applications where that might be viable to have it angled a little bit different to compensate for different, throughout the course of the day, different usage rates. But for the most part, I just want to reiterate southward facing orientation will be the best for us in the Northern Hemisphere. The tilt angle is also important. Like I mentioned earlier, if you lay the panel flat on the ground, it's going to be pointed straight up, and it's not going to be as efficient. What's best if it's directed directly perpendicular at a right angle to the sunlight. And so that's typically what you want to have. For us here in Maryland, we base it on latitude typically, and for Maryland, we're about 39 to 40 degrees latitude. I think I have a map coming up on a slide if you want to see what that looks like, but we're in about the 39 to 40 degree latitude, so we want to have it directed about that angle. You could go a little lower or a little higher without too much change, but that will give you the best efficiency for that sunlight being converted into electricity. If you're too high or too low, you'll see the efficiency start to drop. There are systems that can move and tilt at, of course, an added expense. I've seen a lot of these in Maryland. A lot of farmers have done this. If at least just to manually tilt from winter and summertime. From my standpoint, it's just another thing to keep up with. You know, maybe if you're changing it 3 or 4 times a year to adjust the angle depending on where the sun is during that season. It adds some cost, and you know, some of that equipment will need additional maintenance and upkeep. So I don't always recommend that, but it could work out in some instances. I just personally would opt for savings because I don't see that much of efficiency improving from the tilting, but we'll talk about that as well. If we look at this graph, and I'll mention that this particular simulation for sunlight levels is from Florida, where I'm originally from. So the values will be a little bit different. They're angling, if you look at the roof angles at the bottom, their roof angles are a little bit lower. And why that's important is that Florida is a lower latitude. So they're aiming for a little bit different angles than us. You know, if you remember what I said, we're aiming for about 39 to 40 degree latitude or angling on our panels here in Maryland. But the same concept applies here. And just what I'll show, it's each line on this graph, each color indicates a different roof slope that your panels might be on, 14 degrees up to 30 degrees. And what you'll see is a little bit different electricity in terms of kilowatt hours based on that. And so there's some difference, especially if you look at the left and right side of the graph in the winter season, you'll see that become more spread. It's more significant. Well, I'm sorry, I think I misspoke. On this graph, if you look at the left and right side, this is when the panel is facing north. Okay, so left and right is it's facing north. And remember, you don't really want to do that. You see, for one, the efficiency drops. When you go to the left or right, that means your north direction on this graph, your efficiency drops. And so you really don't want to do that. Where you want to be is in the center of this graph. Right in the center is southward facing. And so if you're facing south, your panel is going to absorb the best light and have the best kilowatt hour energy production. And what you'll see, there's a small difference here. If you're looking in that center of the graph, you'll see a small difference between efficiencies based on angling. So the angle is not super important. It does play some role, and we'll kind of quantify that with some numbers moving forward. But tilt plays a role. Like I said, if the bottom line up here, you see this yellow line at the bottom, you do have a little bit of efficiency drop. If you can see that level of detail on this graph, you do have a little bit of efficiency drop because the angle is so low. Okay, and again, with the extreme case, if the panel just falls flat on the ground and it's pointed up, it's not going to be as efficient. Okay, so you want to stand it up and again match the latitude a little bit better, but there's not going to be a huge difference between 39, 40, and even maybe 45 and 50 degrees. You're going to see that you can deviate from that a little bit. And so if your roof, let's say your roof is not an exact 39 degrees in Maryland, you know, you might go down to 30 and be just fine. You might not see that big of an impact. And we'll talk about some ways we can actually model that. Tilt is important. Let's see, what I wanted to highlight here is the dual axis tracking. So again, the tracking system, if you have single axis, you can rotate east or west, or the dual axis, you can also go up and down from high to low tilt. Again, any of those tilting systems add a cost to the system. If they break, you have to work and replace them. So it's a little bit additional there. Of course, you could see an improvement, 10 or 20% improvement in efficiency, but you also have that additional cost and upkeep associated with it. What I would say is, again, just make sure you're facing in the right orientation, make sure you're close to the ideal 39-degree tilt here in Maryland. You'll see a lot of commercial operations in the map on the right, big utility scale production, so not quite what we're talking about here. But you'll see, even if you look at this map, the utility scale systems are not exactly having optimal conditions either. Some of them aren't at the angle you'd expect them to be, and they're still having quite a bit of efficiency. Of course, in the lower latitudes, like I mentioned in the previous example in Florida, you're going to be closer to 25 to 30 degrees. But we're up here in Maryland, we're on that state line with Pennsylvania, where we're getting close to 40-degree latitude. So again, just make sure you're somewhere around that range. What I'll say is a more important, or equally important at least, facet is looking at shading. This can easily be overlooked, especially with seasonal variation. If there's a tree now shading some of the panels, you're going to get efficiency dropping significantly. In the illustration on the bottom, it's showing that half of the panel is being shaded. If you look at this panel on the left-hand side, you'll see that it's partially shaded. If it's not completely cut off, if this panel is not completely ineffective, maybe it's only working at 50% capacity now. I'll point out the important thing here. Not only is this panel working at 50% capacity, but every panel that's attached to it in series is working at that level. And so you want to make sure that you don't have shading issues or anything like that. It could also be snow cover or anything like that if we have a high snow season. You want to make sure your panel's not shaded or covered in any way. We'll talk about maintenance upkeep with dust and bird droppings and stuff at a later date, but all those things can kind of impact how a panel is producing energy. So as I mentioned, if these are connected in series, what happens to one panel is going to impact the entire series, the entire array. And so I've included some examples here that we talked about last week. looking at different inverters. If you remember what an inverter does is an inverter takes your direct current from the solar PV system, from the module, and it translates that into an alternating current that we use in homes, or the grid system works on alternating current. So we have to have that inverter to make it useful alternating current for different loads. And so in this case, in the top example, you have a string inverter connected to all of these modules. Again, if, let's say, one of these panels was shaded or damaged, now that takes out this entire top row. Okay, and so what you want to do is make sure that, in this example of shading, make sure that you're clear from any obstacles like that. That's just the easiest thing to say, is make sure you're not having any kind of impact like that, because you don't want your whole performance, that whole array, to drop down just because of that. Another option that you'll see is these micro inverters. So in this case, each module has its own inverter attached to it. These are becoming much more common. I think about 40% of the market here in Maryland is micro inverters, and that gives you better control. So let's say your first panel is shaded or it's damaged in some way, the rest of the system will work fine because each one has its own inverter. The optimizer example in the bottom works the same way. It's just optimizing the DC signal. You'll still have to have an inverter with that, but it offers you the benefit that if one of those panels goes down, for whatever reason, you still have a viable working system. You know, I'll say just a quick note on layout. You can look at different layouts, whether you have them horizontal or more upright when you set them up. There's not a huge amount of difference. There could be some difference with shading or snowfall if the snow is collecting at the bottom of the panels. There could be some difference there with what's happening. And what I'll say is, if you have them in this landscape orientation, you may end up in a better situation because of the way that the PV cells are wired up. During the manufacturing process, you have those PV cells linked together from left to right, and so you'll have better connection if some of those are shaded. For the most part, though, again, just avoid any shading issues, and it really won't matter too much. I'm just pointing out some different scenarios that can happen, but really it's going to be site specific and the needs that you have, how you set the system up. Degradation is another important point that I want to touch on today before we actually get into the system design. And if you think about it, no technology, including solar modules, are 100% efficient, and they will also drop in performance over time. And so you have light-induced degradation that takes place. Typically, for your better panels, it's around 0.5% per year in efficiency loss. A higher end model, but a lower quality model, it could be closer to 1% loss in efficiency each year, or even more than that. The example I've included here is from a real study performed over 25 years. You see it's starting at 100% efficiency right off the bat, but it's going to typically, a lot of panels will drop in the first year more significantly than in subsequent years. But after 25 years, this panel dropped to 78.8%. I've heard of a lot of panels performing better than that, but this panel in particular dropped to about 79%. It's still working and operational at that point, and will continue to be operational. And if your energy production has dropped, you could just add another module to your array and compensate for that. The warranty system differs from one company, one manufacturer to another, so just make sure you kind of look into the details of that. Some have used a step model where, you know, for instance, you hit the 10-year mark and then they'll stay, the warranty drops down to 80%. And I'll say that's not too common anymore. A lot of the more recent warranties are based on a linear model where it's just like roughly 0.5% a year. The warranties are getting closer and closer matched to realistic conditions. And so they're obviously not trying to give away free panels if yours drops below 80%, for example. So they really are trying to match up with that. But if for some reason you do drop below whatever your warranty specifies, So in this example, let's say it dropped down to 79% after 25 years, they'd likely replace that panel because if that was how your warranty in fact read. But just know that the efficiency of any module will decline over time. Now, with the time that we have left, I'll quickly touch on how we actually start to design the system. And we started, if you missed at the beginning, we kind of talked about energy use and how much energy we're actually using. Again, whether you had an energy audit done or you're quantifying a specific load, let's say you wanted to drive an electric fence or whatever it might be, that's kind of where you start on this. And then we'll go through some different technologies and techniques, and we use a piece of software online that we can kind of start to design a system around those needs. So again, going back to how much sunlight is available, I've included a map here from NREL again, and this gives us the total sun hours that are available in specific regions. I've blown up the Maryland region so you can see for the example that I'll work through today, I've highlighted the Western Maryland Research and Education Center that I'm housed in. That's where I'm sitting now. And what you'll see, it's in the Hagerstown area of Maryland, if you're not too familiar with that. If you look farther to the west in Western Maryland, out towards Garrett County, and you'll see you're up in the mountains in that far western region of Maryland. So you have a little bit different solar resource out there because you're in the mountains and you have different weather and climate patterns there. You know, on the eastern shore, when you're out by the coast, you're going to have different environment out there. But what I've highlighted here is for my office and doing a site assessment for this. So based on this map, I can see what the total sun hours are, and in this case, it's in that kind of greenish region. I've blown that up here, and what you'll see is I've indicated that with a star on this scale. So this is just a closer look at that, but it's about 4.1 kilowatt hours per meter squared. So that's the solar resource that I'm going to use for this example. Now, the math that I'm showing here is just a basic estimate. We'll go through a very simple example just to get a ballpark number. Now this equation is not, I don't say take this to the bank and invest in the system. This is just, again, a quick estimate that we can make of a PV system that would suit our needs. So in step one, first what I'm doing is I'm taking that total sun hours that I have available here in the Hagerstown area. It's 4.1, and I am multiplying that by 365 to get the total annual energy available from the sun. So in this case, I come out to almost 1,500 kilowatt hours each year. So that's the first, we start understanding how much sun you have available. Step two, to actually calculate the size of the system that would supply that. And so starting with this, if you look at that number on step two, 5,592 kilowatt hours, that goes back to the example I started with at the beginning of our program today. How much energy I'm using, this was on the electric bill. Okay, and so if you look at the far right, you'll see I've just summed all this data up for the entire year, and that's how much kilowatt hours. In this case, it's pretty small. This is probably for an apartment size. My personal house, we use a lot more energy than that. You might be closer to 10,000 or more. But this is for the energy use of an example here, 5,592 kilowatt hours being used. I multiply that kilowatt hour by 1. And the reason I do this is in this example, I'm going to say I want 100% of my energy to come from solar PV. If you only wanted to, for whatever reason, only do 50%, let's say you don't want to invest in a full system, you just want to offset some of your energy use, you could do 50% or 0.5. I've used 1, it makes the math easier here, but 100% of my energy. On the bottom of the equation here, you're going to have where your sunlight hours comes into play. So in this case, you know, the number I got above is 1,497. And there's an efficiency factor in there as well, the 0.8. 0.8 is coming from any efficiency losses that you have in the entire system. Now the panels, when you buy a module, those already have an efficiency rating on them. We looked at that last week in our webinar last week. This efficiency rating here that I'm using, 0.8, is a pretty conservative estimate for the losses that you'll have in the wiring, the inverter, and other parts of the system where you are not working at 100% efficiency. And so 0.8 is pretty conservative. I'll share where some of those numbers come from momentarily, but I'm using a conservative 0.8. So run those numbers. And in this case, your output comes from, assuming I've done the math right, is a 4.67 kilowatt solar PV system. Okay, and so if I'm supplying 100% of that energy need that I got from the bill, then I would design a system that's 4.67 kilowatt, and that's a power rating. That's typically how panels are referred to, or a solar system is referred to, is in terms of the power. Just for a frame of reference, those larger systems, the utility scale systems in the state, the big solar farms, what we often call them, those are typically in megawatts. You know, you're talking about 2 megawatts, 5 megawatts. This is a much smaller residential example, and so we're still in the kilowatt range, but 4.67 kilowatt system. Now the third step here is just how many modules you need to get, or panels if you want to call them that. So we take our power for the entire system that we need. We needed 4.67 for the power rating. And this example, I'm looking at a 300 watt module. So just divide by 300 watts in this case. If you have a smaller module, 250 watt, or maybe you're buying a 350 or close to 400, you could do that as well. You do have to look at what the panel is in. The panel, again, is in watts, so we have to convert watts to kilowatts, and so it's an easy way to do that. If you crunch those numbers, what you come out with is you'll need 15.6 modules to supply that energy. Okay, so 15.6 modules of energy. Of course, you can't have 0.6 modules. So if you want to make sure that you meet all of that energy demand, you'd round up to 16. If you round it down to 15, you might be a little shy of that 100% that you're trying to provide. But you can use this. Again, this is kind of a ballpark estimate. We'll look at a more specific and robust way to evaluate this. But as I mentioned, with that efficiency rating, or what's called the D-rate factor, or D-rate value, is based on any efficiency that's lost in the system. So you'll see various things like the DC and AC wiring, shading, anything that's happening there in the system will have a loss of production associated with it. So in this case, they're using an example 0.7 or 70%. In the example I just shared with you, I used a conservative 80%. It's kind of the same idea there, but I use the more conservative value, and kind of gives you an estimate. Now, I know we're kind of running low on time, but I just want to touch on some of the inverter aspects as well. And so when you go to select an inverter now, the inverter, remember, it's receiving the direct current that comes out of the panels, out of the modules. And really how you can size an inverter to work with those panels is based on the voltage. And so typically when you look at an inverter, it's specified to work within a voltage range, from a low end of the voltage up to a high range of the voltage. You want to make sure that you don't send too high of a voltage into the inverter, or it'll fail. Or likewise, if it's too low, your inverter is going to be expecting a certain voltage from the panels, and if it's too low, your inverter is going to shut off. And so you want to make sure you're within a proper range. And just one quick thing that I'll try to point out here before we kind of start to wrap up is the temperature effect on voltage. If you remember from what we talked about last week, the temperature of the panel actually affects its efficiency. When it's much hotter out, higher temperatures, you're going to get a lower efficiency and a lower voltage. So it kind of works counterintuitive to what you might think. At colder temperatures, the performance of a solar PV system is much higher. Your module is much more efficient at lower temperatures, and so you'll get higher voltage. So I just want to point out the importance of picking out, when you pick out the inverter now to match this PV system, the solar modules, you want to make sure that you're within the proper voltage range. And to do so, I typically look at the temperature range, So I'm going to share a brief example. I won't spend a whole lot of time on this, but if you look at the, I use the most conservative temperatures that I could find for this example. So I looked at the extreme high temperature that we've had in my area, and this is for Hagerstown. I've also pulled up the lowest possible temperature, which is negative 16 degrees Fahrenheit. That was back in 1994. So this is a very conservative evaluation here. I'm hoping we don't ever see that temperature again. I don't prefer to live in that environment, but a panel will work pretty efficient at these lower temperatures. But these are extreme temperature conditions that will impact the performance and efficiency of the actual solar module. And so I'll kind of just indicate, we won't go through all of the math associated with this, but there's another good assessment on the performance of the panel and how much voltage is actually coming out of the panel based on that temperature. So in this example, I'm trying to evaluate what the maximum amount of voltage is. Remember, if you look at the back of a module, let's say you've just bought a PV module, you look at the back and look at the spec sheet. So in this example, you'll see they've highlighted that the voltage here is 47.2 volts. That's open circuit voltage, no loads attached to it. That's the highest voltage you're going to get. But that, again, is tested at the standard test conditions. We talked about that last week. Standard test conditions are like 77 degrees Fahrenheit, kind of an ideal temperature. I think that's what it is here today, but mostly we do not have temperatures like that every day. So we're going to compensate for that temperature and see what the voltage, what would happen to the voltage in more extreme temperatures. And so that's what I've done here. I've taken in that absolute minimum temperature from back in 1994. So this is kind of an extreme case, but I've put that in there, and that's how we kind of compensate, and we compare that to the testing conditions that all modules are tested under. And so we can kind of compensate for the temperature that way. And so I'm not going to run through the whole math of this. I've provided all the steps here. If you want to check my math and see if you get the same thing, you're welcome to do so. But again, at low temperatures, you're going to end up with a much higher voltage. And so this case, it's about 15% higher than what's stated on the spec sheet, just based on that temperature. So again, the point of sharing this example with you is if we're operating at different temperatures, we're going to get a different voltage coming out of the PV module. And we want to make sure that doesn't damage the inverter. So how many inverters would that work with? Or how many modules would that work with? I'm kind of sharing an example here. If you look at the details for the inverter that I selected, it works in a range of 240 volts up to 450 volts. So we have to make sure we're within that range for the inverter to work nicely with this system that we're setting up. So at the bottom here, you'll see I've taken the higher end of that range that the inverter will accept. We don't want to go over 450 volts or it could damage the inverter. And so I'm dividing that maximum threshold from the inverter by our maximum voltage that we can get out of the DC, the direct current out of the panel. And so in this case, I could do 8.3 modules hooked up in a series without damaging the inverter. Now you typically want to round down just to be safe. If you round it up to 9, for instance, you'd exceed that voltage and you could damage it. Now, of course, this is dependent on temperature. You're not likely to get up to negative 27 degrees Celsius. So you're probably not going to, it was negative 16 Fahrenheit, I think. So it's probably not going to be that cold ever, but this is a really safe way of looking at it. So that's just an example. Whether or not you caught all of the math is another story, but you can go back and review if you really are interested in that. This is just the flip side of that. And so I'm looking at this case at really high temperatures. So in this case, the only difference is I've kind of changed the maximum temperature and I'm using the voltage at maximum power. Okay. And so this information either, this maximum temperature comes from the weather report that I'm using. The maximum voltage comes from the back of the solar module. Likewise, you can get the output of that is almost 31 volts. So that's probably the lowest that you'd see coming out of this particular module that I'm looking at. Again, if you were to determine how many modules would work with that, you could divide the voltage by the modules. In this case, you get 7.8 modules. In this case, you'd be better to round up. So in this example, we kind of evaluated the lower and upper voltage ratings that would work with this inverter. In this case, it works out to 8 modules. So it would be pretty safe to hook up 8 of these modules. And this is the model that I'm looking at is a 350 watt solar module. And I could hook up 8 of those safely into this inverter that I selected. So I could share more details if you're interested, but I know I'm kind of low on time here. I'll briefly share a more robust tool at getting a better estimate, and we'll kind of use this website moving forward in some of our upcoming webinars and evaluating different systems. This is what is called the PV Watts calculator. Again, developed with National Renewable Energy Lab. The website is provided here, and I'll quickly show you some of the detail associated with that. What you'll see is, first of all, it's asking for your location, so you can put your address in or your zip code, provide some information. It'll have your Google map here, and you can actually even highlight a region that you're interested in on your property or a rooftop system, and you can kind of get specific weather data and specific information from that. For the system, I'm not going to go into too much detail, but I kind of put a similar example to what we've worked out by hand, and you'll kind of wonder, well, why did I make you do that? We could have just gone straight to the system. I did see some value in kind of looking at it from a fundamental level, and again, that's a quick way to kind of get some values. But if you want to play around with this system as well, before we come back to it in our webinar, you're welcome to do that. But you can put in the size of the system. In this case, I put in, I can't see that value necessarily, but I think it was like 4.6 kilowatt system is what we modeled. And so I've put some of those similar values in. I left some of those values as they are. I left it at 180 degrees southward facing. I think I put rooftop system in there. In this case, we don't get exactly what we did on paper. What we got here is 6,200 kilowatt hours per year. So this is a more robust way of looking at it. And so I encourage you to use that website, and I've included some additional resources here, and we'll kind of touch on these in subsequent programs as well, in my backyard and my solar estimator, some other useful tools. But again, explore that PV Watts, and you'll find some useful applications for that. So with that said, I'm gonna pull up our final survey as we kind of close out, and I'm gonna get your survey started for some more input, and also take a look at the questions that we've been getting. So if you still have questions, continue to get those into me as well.